So here we want to provide solutions to quiz number 3. And we're going to make 2 recordings, one for problem 1 and one for problem 2. So in problem 1, we have this point P, which is at these positions x equals 2, y equals -2, and z equals 3. And I'll note that in the other paper homework solution, I've put the point P at the wrong place, but it won't matter at all for the formal aspect of where we're doing things. And we have this surface density sigma, which is in this blue box that I've drawn here. And sigma has the functional form of, has the functional form of 2x squared y. And it's existing in this blue box at these locations here. So now I wrote on the board that you can always make the separation vector r that I've drawn here be provided by x minus x prime, x hat plus y minus y prime, y hat plus z minus z prime, z hat. And in this notation, P is going to be at x, y, z, and the prime variables are where the charge is located. So if I go ahead and put in my value for P, see P is equal to 2 and y is equal, for P, x is equal to 2, y is equal to -2, and z is equal to 3, then this vector r is 2 minus x prime x hat plus -2 minus y prime y hat plus 3 z hat, because z prime is equal to 0 here. And then once I know that the magnitude of the separation vector is the length of this vector. So that's the square root of 2 minus x prime squared plus -2 minus y prime squared plus 9. 9 is 3 squared. And then r hat is going to be it's going to be 2 minus x prime over separation vector magnitude x hat plus -2 minus y prime over separation vector magnitude y hat plus 3 z hat over separation vector magnitude. And that's useful because if this little point here is creating electric field at the point P, then the little bit of electric field is given by 1 over 4 pi epsilon naught dq over r squared separation hat. And so now I basically have all the pieces that I need. My dq is going to be equal to sigma dA. And I'm going to go ahead and start putting primes on my sigmas and my dAs. So I'm going to write dq is 2x prime squared y prime dx prime dy prime. And now we simply have everything we need to just write out the integrals. So the x component of the electric field will be 1 over 4 pi epsilon naught. The integral of dq, and dq was 2x prime squared y prime times dA, which was dx prime dy prime. And in order to get the x component, I need to have a 2 minus x prime. And all that is going to be divided by 2 minus x prime squared plus -2 minus y prime squared plus 9 to the 3/2 power. And the reason I have the 3/2 power is that I'm going to have the dq over r squared times the r hat, which was for the x component, would be 2 minus x prime over r. So that's going to give me separation vector cubed. And so that's to the 3/2 power. And here the x coordinate is running from -1 to 1. And the y coordinate is running from -2 to 0, because those are the locations where I have charge. So the key here is, once you can write down what the separation vector is equal to, then you know what the separation vector magnitude is equal to, and you know what the unit vector in that direction is equal to. And so, again, you can just write down all three integrals. The integrals will all have the same limits because we're integrating over the same charge distribution. And the only thing that's different is what I'm putting in to pick up my directions. And what I'm picking in to pick up my directions are these top parts of the r hat. So 2 minus x prime squared plus negative 2 minus y prime squared plus 9 to the 3/2. And then the z component just follows. I just need to grab the z part of the separation vector, which on the top was just a 3. I'm integrating all of them over x prime and y prime because that is where the charge is located. And when I do so, the x primes and y primes in the bottom and the top will all drop because we're doing definite integrals over them. And those are the 3 integrals that I would need to do in order to compute the electric field at this point, P, which was located at 2 minus 2, 3, for the sigma in the blue region. And the blue region is showing up in the limits of integration. The x, y, and z components are showing up in terms of how I made use of r hat, and I'm integrating over where the charge is located.